this reason, okay, next topic we are going to consider is the causality. Okay. What is the causality?
Let me show you the slide again here. If the signal is called causal signal, that means if I have an input, and suppose this is my input, and then the system does not have any response before this time. This is the initial time. Okay? Before the initial time, the system output is zero. It's nothing. Maybe it's better to call it nothing, but not zero. Okay? Nothing here. Nothing here. Only after the initial time, we have an input to the system. Then there is output after the initial time. This kind of system is called causal system. In Chinese, we call this 因果关系. 因果关系. We have a reason, in, we have an output, we have a果, output. Okay? There is a causal relationship. But for the non-causal system, we have an input. At this moment, we have an input to the system. But if the output has a response, even before the input time, there is an output coming out from the system. This kind of system is called causal system. For example, the stock market. Okay, in the past week, there's a big issue, right? The American government, they want to tax our import or output, whatever, the goods. That causes a big problem. Now, if you are somebody, let me say that, and you have a channel to learn to know the message earlier than any other one, then you are going to have certain action. Before Trump decided to increase the tax, but because you have an internal channel, coming from somewhere, you start to even maybe dump your stocks or buy some stocks even before the Trump announced the tax increase. Okay? So this kind of behavior is called non-causal system. Non-causal system. In the stock market, this non-causal system phenomenon happens a lot. Okay? But for a physical system, we don't have that kind of non-causal phenomenon. Okay? That's a very interesting phenomenon. Then what do we do with this causal system and causal signal? Okay, maybe raise up this. Okay, now let's assume we have a system, h of t, then the output y of t will be the convolution of the input and the impulse response of the system, right? Okay? Now, what if my signal is causal? what if my system is, my signal, if x of t is 0, when t is smaller than or equal to 0. Okay? Yeah, that's enough. If x of t is 0, when t is negative, then the lower limit can be replaced by 0. Okay, this is the total signal. Smaller than that, sorry. So if the signal, then the lower limit of the integration can be replaced by 0, right? Because this is the integration of x of t of tau times h of t minus tau. Okay, now furthermore, if if both the signal are causal, so this is the total system. If both the signal and the system are causal, then not only the lower limit is replaced by 0, but the upper limit is replaced by the time. T, the current time. You don't have to integrate up to infinity. Only integrate up to now. Okay? Don't have to integrate up to the future. Okay? Because we are considering, if we are considering total systems. Okay? Got it? Right?
Okay.
So that's the point of total system, and that's it. No big deal. Sorry. Okay, any question up to this moment? Okay, so let's move on to the next topic. Next one, since we have done the convolution last time, so I'm going to skip this graphical computation of convolution. Okay, we have done this one last time, so. Okay, so I'm not going to repeat that here to save a little bit of time. You can read it myself. If you have any question, let me know. Okay? If you have any question, let me know. Because we have done this last time. I'm showing you this. Remember? Suppose I have two functions, the blue one and the red one. Then the convolution of the two functions is this kind. Okay. And similar for the next one here. Now the main idea, okay, let me just use 1 minute to replace this again. Then we skip this later. The main idea is if you have two functions, say f and g, say f and g, you want to convolute f and g. You want to convolute these two functions. The first step is to flip. Suppose we want to flip this one. Flip g of tau, g of t. So we flip this function around the y-axis. So we have this g of negative tau, okay? And then you move this function, okay, you flip this to here. Then you move the function to the left. I'm sorry, to the right, sorry. So you have g of t minus tau, you move it to the right. So you move this until they have an overlap. Okay, now you can see that they have an overlap. And you have to compute the product of this area, the product of this in this area. Okay, f of tau times g of t minus tau, okay, inside the overlapped area. Okay, and you compute the number. And then you move the area again to the right. Again. That's what we did in the convolution. Okay, that is the cartoon or animation shown in the previous video. Okay? So that's the basic procedure. That is the basic procedure. Okay, I think that's it. Okay.
All right, and then another topic is about the
Stability. Now here we consider bounded input, bounded output stability, but actually later on for nonlinear system we are going to use the eigenvalues of the system to determine the stability. But anyway, let's follow the book, follow the textbook. Okay, now suppose we have a system. Okay, in this course, currently we can see the linear system. Now, if I have a signal, x of t, this signal is bounded, means it has a finite amplitude. Okay, there's upper bound and lower bound. Usually we use only the maximum, the biggest. Okay? So x of t, absolute value is smaller than, say, m, whatever. Okay, for all the t, then we want to know whether I have y of t is also bounded by the street. And we use a k, k is finite. How do I determine this property? Why I have to know this? Because we need to have a stable system in order to control the system. Basically, that's it. Okay? So why we have to know the stability? Okay, we need to know the stability. So that we are able to control the rate. Okay, maybe this is too rough, but that's fine. Doesn't matter at this moment. If I use a two-dimensional figure to show you, that would be for two-dimensional circle. If my input is always bounded by the circle. Okay, if this is, do I have the result? The output is also bounded by the circle. Okay, if I have a two-dimension. So how do I determine this? How do I determine this? We call that, well, P is the evolution of the impulse response and input. Okay? Now, if the input x of t is smaller than n, smaller than or equals to, that's fine. Then we put equality here. That's the dimension, okay? N times h of t minus tau equal. Okay? Then I can take out the n out of the equation. Okay? And then this also equals to n times the integration of the impulse response. So in order to have a finite, output, this integration of impulse response must be finite, right? Okay, so let me get this. If this integration of impulse response is finite, now this result is quite general, but sometimes it's useful. Again, like I said, for linear system, eventually we are going to consider eigenvalues of the system. Okay, we don't use this integration of the impulse response. It's not convenient for us to design the controller. Okay? Okay, now here we have a quick example given by the book. So let's use the example directly. These are this. Initially, the current is zero. Now here, let's assume the input is a development. So So we have to solve the equation, differential equation. We have an input. Can anyone solve this equation? We have taken a course, ordinary differential equation, last semester, right? How do we solve this equation? Okay, Laplace transform is one of the methods we can implement. Any other suggestion? Using the integrating factor, right? Okay.
So,
What is integrating factor? You have to multiply it by, say, negative t. So let's multiply the entire equation by u. That's the integrating factor. Okay.
then we have
The two terms on the left hand side actually can be merged as one term. T over
Q over T,
of
e to the T times L, right? If you differentiate this function, you have e to the T times differentiation of, right?
LT
And then
plus LT times the differentiation of e to the t, that is e to the t again. And then equals this one. Okay? And then we integrate both sides. Okay, and we want to start from 0 to some other time, some arbitrary time. Okay, maybe we need to be careful. We start from 0 minus because we have an impulse response. Okay? Well, I'm not going to teach you how to solve this, so I need a volunteer to do this for me. Any volunteer? Gentlemen, could you finish this for me? We are here already. Come on, come on. Now, lady, how about you? Try it. Okay? You have taken a course, right? Last semester, just a few months ago. Come on. Almost there. We are almost there. Okay? Okay, good. Thank you. We are almost there. Okay? All right, thank you. You all forgot.
we forgot. We seldom use this.
You don't use this. But there are many other methods, I know, but this is one of them.
That's one of the basic techniques we have to know. Okay? Now the input B sub S is the Gilman function, so here.
We have already there, so we can start from here. And we have modified the equation by integrating factor already. Okay, so here I multiply the entire equation by the integrating effect. Remember this, gentlemen? Yeah? You forgot. Yeah, please. Help your friend. Anyway, this V is still a function, so it make your life easier. That V is already a Taylor function. The input. Okay, you can take the advantage of this. Remember the property of the Taylor function. The integral of the Taylor function is equal to 1 if you integrate from negative infinity to positive infinity, right? If you multiply the Taylor function by another function at a point, at a certain point, you have a Taylor function, then the integration will be the function value at that point. Are you sure? That's a Taylor function, okay? Be careful. No, come on. No. Be careful. You got something, but be careful. Differentiate the Taylor function, let me tell you that. Because the differentiation of the Taylor function is a terrible stuff. If you don't have to differentiate the function, it's already the integration of the Taylor function times another function, right? I have mentioned that in it. Remember the property of the Taylor functions. Sorry. No, young lady, do you remember the same one? Hello? This one?
The property of Taylor function. Okay. I proved this for you in the class a few weeks ago.
Come on, I have done this for you a few weeks ago. Do you remember that? So use that 0 minus a little bit smaller than 0, just for safety. What's this? Hey, come here. Almost there, okay? You don't have to erase that, okay? Come on. Almost there. Come on. Come on, aerospace engineer. Again. What is A here? Okay, thank you. Oh my God. You have to practice, okay? There are lots of important things you have to remember. All right, so let's look at the left-hand side. Okay, dt cancel out dt, so that's the integration of this function actually. The d of this, and then take the integration. So that would be equal to
e to the t times I from 0 minus 2t, and then
equals to the integration of the right-hand side. The reason I put the 0 minus is I want to include the 0. So let me show you. Let me draw this one here. So this is t, and this is 0. Okay? And the lower limit of integration is 0 minus. 0 minus. Smaller than 0. A little bit smaller than 0. This means 0 sup minus means a little bit smaller than 0. So we integrate from here to arbitrary time t, and we have a Dirac function at 0. So you are right, there's a Dirac function here. Okay? So we have a Dirac function here at 0. And then we want to multiply by e to the t. So the integration of value at this point.
so the e to the
Because 0 sup minus, it is a little bit smaller than 0. So this interval covers this point, covers this point 0. Okay? So the left-hand side is simply 1. I'm sorry, the right-hand side is simply 1. Okay, and then what about the right-hand side? We have e to the t times e I of t minus e to the 0 times I of 0. Now, since the initial value of the current is 0, so this becomes 0. So we have I of t equals e to the negative t. So this is the impulse response. Impulse response of the system. So the impulse response will be
negative. So the output will be exponential decay function e to the negative.
So now we have found the impulse response.
But this is the h of
E.
What is h of sorry. What is h of t?
The impulse response. And now we want to determine the stability. Okay.
To test stability.
We want to integrate the function. Now, since this is a causal system, we start from, we can see the only causal system. So actually,
The lower limit will be 0.
because we are considering causal system, we start from the time 0. We start from the time 0. It's a causal system. So now,
The integration of
e to, okay? And so we have negative e to the negative infinity minus e to the 0. So that's equal to 1. Okay? So this is the finite number. So which implies the system is stable, is always input volume over EIPO FIFO system. Okay, only input, only output schedule. Got it? Okay? Got it? No? Not really. Which part? Do you know how to solve the differential equation? Do you have a question about the differential, solving the differential equation? Sorry? You don't know that? Not really remember. Come on, you just took the course a few months ago, right? Okay, I'm going to ask again, what happened? He told you this, right? Who told you ordinary differential equation? Who? Who can you know? Not Hong Professor Hong no? And who told you ordinary differential? You don't know the name? Oh yeah. Anyone else? No? Well, another one. Not from my our department. From our department, or not from our department. From our department. Well, come on, who was your instructor? You look, remember, come on. Oh well. Okay, anyway, whatever. Okay, you are supposed to know that one more time. Any question regarding the differential equation and the conclusion here? Actually, for this system, the eigenvalue is negative. Okay, you haven't talked about this. It's on the left-hand side. On the left hand. So it's a stable system. Okay, if you look at from the eigenvalue of the system, that's also one way to determine the stability of linear system. Okay, all right. Okay, let's move on to the next part. Okay. There's another example, I think, due to the time limitation, I need you to read. It's very easy. Okay, please read it by yourself. For this one, it's a positive feedback system. Okay, the conclusion is it's not a FIFO system. It is not a FIFO stable system, excuse me. Okay, but you have to read it by yourself, all right? Please read it by yourself. If you have any question, let me know. Okay. We had done a similar example last time, so let's skip this one. Okay. How many minutes? Okay, I think that's good enough for this example. Okay, could you open your laptop? Let's run this example. And we start here. Okay? Run this example now, please. Open your laptop computer, please. Run this example. You see what happens. Okay, this small example, so I think we have enough time to do this. So please run the example 2.13, approximate convolution interval. It's on page 165. 165. Okay?
You can copy the code directly from the record notes, but I had to make a few changes because of the character, one character to be created. time storm that will leave your life. Now what do we have? Okay. Try to understand what this code is doing, okay? Not just duplicate the code, that's it, okay? Try to read it and understand what is going on behind the code. This code is for the example 21.3 in the textbook. Okay, so I highly recommend you to look at it. Have you finished? Not yet? Okay, do it then. Okay? Make sure you know what's going on here. If you want time, you may leave the class now, okay? Because the power is going to be shut down later. Yeah, try to fix it on the platform, okay? All right, I think we're almost running out of time. The power will be shut down later. So please do this at home. Do this at home. Try to finish this at home, okay? You can finish it. Okay. Yeah. Try to fix it. Okay, I think time is up. So we have only 1 minute left. Okay, we are going to lose our power in 1 minute. So try to clean up everything here. And finish at home. You have to finish it now. Finish the random form.